So today in this video we will just do one simple topic, that is transformation. And actually the transformation is done by the Schrodinger. We will actually transform the time dependent to time independent. Basically we will just remove the factor of time dependent to time independent. So let me write the first time dependent equation first. So it's minus h square by 2m dou square by dou x square psi x comma t equals, actually it's plus vx psi x comma t equals to iota h cut dou by dou t psi x comma t. Now you can see over here that this term, the psi, that is the wave function, is depending on both, like x is basically the momentum and t is the time. So if mathematically we can write it as this as well, because both are the same things. So what we will do is we will write the same thing just by separating the value, that is psi x psi t plus vx psi x psi t equals to iota h cut dou by dou t psi x, and the same way psi t. Now there's one simple like mathematics that would be known to everyone, that we assume in physics. So what we're going to do is we will divide this whole equation by psi x and psi t, and then after doing that we will just rearrange it so that all the same components will be on the same side. Now if we do the same thing, so minus h square by 2m, no value. Now over here we have a differential of x square. So what we do is we will divide it by t, there will be a x over here, so 1 by psi x dou square by dou x square dou x plus the whole thing will be cut off bx. Hope you understand, like you will divide this by this and basically this will be cut off, and this is a under this partial derivative, so we can do that over here. Now iota h cut and this thing goes the same, so we have psi by psi t dou by dou t. Now you can see like this is totally dependent on time, and over here you can see the position. So here we just rearranged in the same way. So as we know that this is a partial derivative, this whole thing is a partial derivative, so it basically have more variables to store, but right now it has just single variable, so we will just change the partial derivative to ordinary. Okay, so what to do is this term first, we will write this term. So let me remove this, and iota h cut 1 by dou t d by dt, and okay, this will be termed as b. Okay, now this term is b, and if I iota h cut, as this thing is the same, so dou f by f equals to b dt. And then we know this differentiation is basically ln of f bt plus c. This is the constant, and t is basically this thing. When we differentiate, I mean integrate, then ln f equals to bt, and this thing over here iota h cut, and then we will just have the value of f over here, and this log n will be over here, so it would be going to its bt by h minus. So we'll just, the iota will be in the numerator part, so we will add the minus sign over here. Okay, so now this, we have to remember this thing, and if I say like this, it's the same thing. We just take the whole thing as f. Now comparing this thing to a free particle is itself a big thing. So what we do is psi x comma t, that is a time dependent, and it's more or less equal to h cut pt minus of px. Over here you have the uncertainty over here, so energy, time, momentum, and position. The b is h cut by omega equals to t, basically, or the same thing. And then iota h cut, the same thing that we wrote, the first thing, that is 1 by psi t dou, like d by dt, and then dt equals to e. Now what we're gonna do is, let's equate this equation as equation number 1. Now what we do is, we will substitute this RHS, the RHS, to equation number 1. So this thing, that is the RHS on that side. So if we equate minus h square by 2m d square by dx square psi x plus bx psi x equals to e of psi x. So here you can see that this is the whole equation, which is dependent on position, and this is the energy operator. So if I just recap all over thing, so this is the time dependent equation, and this is the time dependent equation. And then what we do is, we will just divide it by, we just separated the x and t because they are both in multiplier currently. Then we will divide this whole thing and rearrange such that the whole position operator are turned into this way and the time is cut off this way. Okay, now what we see is that, as it is, it's like the base maths, that we change the partial derivative to ordinary derivative. Okay, now as you can see, this is the position derivative, so we don't have to bother about this thing. So we will take this term and carry on with this. So first we take it as to b, then we make everything as f, differentiate by f. What we do is, the side t equals to, so this is the whole sequence that we got. Then we just differentiated a bit, we got this value, and then as f is psi t, we got this value. And now comparing to the free particle that is given by this equation, if we put that, we know that b equals to h cut by omega, and that h cut omega is basically E, which is the total energy. And now if we equate the b value that we got equal to E, which is the right side, equating, then we got this value, and that this is time dependent Schrodinger wave equation.